Good. Now, so today we are going to discuss the conduction abnormalities, and if you do have any question, please ask me. So far what we discussed, that's the arrhythmia that could be specified due to impulse formation abnormality. This is what we discussed so far, all right, the last time. And we could have a conduction abnormalities, meaning that we do have a normal impulse formation. However, sometimes the impulse is not propagating to another point, another part of the ventricle. And this is called the conduction abnormalities. We can have, let's see, the blocks, and we can have a faster conduction, that's be the pre-excitation syndromes. Now, based on the severity of this conduction abnormality, we are going to talk about grade 1, grade 2, and grade 3 or total block. What does it mean? It's meaning the first degree block, second degree block, or the third degree block, or the complete block. And we can talk about not only the severity, but we can talk about the location when the block occurs. Now let's see the types of the blocks. First of all, we do have a connection between A and B. A and B represents two different parts of the heart. This A can be located in the atrium and B can be located in the ventricle or inside the ventricle or and so on. This is what the location is, the different one. But let's see the severity. First of all, there's the normal. When we do have a certain velocity, we do have a certain propagation of the charge. What will happen when we do have a first degree block or grade 1? It meaning that we still have a connection between A and B. However, the impulse propagates slower to the B. So every impulse that rises in A getting to B, but slower. What do you think? Is this rhythmic or arrhythmic?
It's rhythmic.
Exactly, that's rhythmic because the conduction speed is not changing. That's B constant, but slower. Now, what will happen when we do have a second degree block? Second degree blocks means that we do have a connection and conduction between 2 points. However, sometimes the blocked, so it's not propagating from one point to another one. However, by definition, so you said mostly conducted, but sometimes not conducted. And whenever we do not have the conduction, that makes it arrhythmic. So these second degree blocks generate an arrhythmia. Now, the second degree by definition means you cannot have more than only one dropped beat between two conducted ones. So you cannot have two unconducted and so not conducted, not conducted, conducted, not conducted, not conducted, conducted. This is not a second degree. Only second degree conducted, conducted, not conducted, 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 not conducted, 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 conducted. So that's the meaning, all right? Is it clear?
Yes.
Yes.
Good. Level 1. Now, second degree AV block has two types. Basically, this is what means that Mobitz type 1 or Mobitz type 2. Now, Mobitz type 1 means that the speed of the conduction is gradually worsening, and after we do have a drop beat and start everything from the beginning. It looks like as an old man is walking on the street, and when he gets tired, sitting down a little bit, and after start again with very freshly, and is getting tired and start again. So by definition, this you should remember. The last conduction time is longer than a first conduction time. So relatively, the first conduction is faster than the last one. So the interval of the last one is longer than the first one. Let's see. So starting normally, getting slower, slower, and after we have a puff bit, and after start, everything from the beginning. All right? Clear?
Yes.
Yes. Okay. Mobitz type 2. Mobitz type 2, when the conduction speed does not change. Whenever the charge conducted to one point to another one, it has the same velocity, always the same. Can be normal, can be slower, can be whatever. All right. And however, when you have a bit, is not conducted, and after conducted, conducted. So if you look at the last conduction time, is the same as the first one. So there is no changes in the velocity or in the distance between these 2 points or time or between these 2 points. Next one, these 2-to-1 blocks. Now, why is it important, this 2-to-1 blocks? Because 2-to-1 blocks is the highest second degree, because we do have only one dropped beat between two conducted ones. However, this can be Mobitz type 1 or Mobitz type 2, but we cannot differentiate because the last conducted and the first conducted distance or the time the same. So, and that should be rhythmic. As you see that every second beat is not conducted. That is rhythmic, but this is usually slower one. Okay, good. Now, the high degree. We do have the high degree. By definition means that mostly there is no connection between these 2 points, but sometimes it's still conducted. So, not conducted, not conducted, not conducted, not conducted, conducted, not conducted, not conducted, conducted, not conducted, not conducted, conducted. So, this is a rhythmic, and mostly there is no connection between these 2 points, but sometimes it's still conducted. So, that makes it a rhythmic. However, if you do not have any conduction between these 2 points, that's a patient won't survive it unless we do have a lower center that starts to fire. So mostly in these high degree blocks, we do have an escape rhythm, and this escape rhythm is interrupted by some conducted bits. So if we do have arrhythmia, but mostly arrhythmia made by the conduction. All right?
Can I
Now,
ask a question?
yes.
Is it still second degree AV block?
No, that's a high degree. This is why we said high degree, because a second degree, by definition, we can have only unconducted between two conducted ones. So that's a different entity. This is between the second degree and the third degree. That's what's called as a high degree. Okay.
Okay, thank you.
Now, let's see the third degree blocks. No, that's a simple one because there is no connection between forever between 2 points. And escape rhythm is going to save the life of the patient. So if you want to say there is no connection between A and B, that's it. Now, let's talk about the type or the location. The location can be, where do we have conduction? We do have conduction between the SA node and the atrium. Okay, if you look at the SA, do we have any ECG sign of the SA activation? When the sinus is activated, do we have any?
No.
No. So relatively, we do not see the sign of the A. What could be the sign when the charge, whatever, reached the B? That the atrial activation. And that should be the P wave. So here we have to rely only the B point, how we diagnose it. The simplest one to understand, the AV conduction abnormalities, because we do have an A such as a P wave, and we do have a QRS as a B. So we are going to evaluate the connection between the P wave and the QRS complexes. So that's a simple one. Mostly the duration of the PR interval that represents the conduction between the atrium and the ventricle. This is the simplest to understand. This is why we should start with this one. Now, an intraventricular, when we do have the block usually in the bundle branches, so relatively in those part of the ventricle is not activated normally. So what will happen? First of all, the width of the QRS complex is be wider, plus the normal shape of the QRS be altered. So the shape and the duration of the QRS complex be how we diagnose these intraventricular conduction abnormalities. Now let's start, as I said, the AV conduction abnormalities, because this is the best and this is the easiest to understand these different types or different severity of the block, such as the first degree, second degree, Mobitz I, Mobitz II, high degree, and so on and so on. All right, so let's start. When we do have this AV block, okay, we can have anything here. Good. Let's move on. What about the first degree AV block? The first degree AV block means that every P wave gets conducted but slower. So the RR interval equal with the PP interval and the rate is unchanged. So that's relatively is rhythmic. So, however, the PR intervals are prolonged longer. Now, what's going to alter the PR interval? Can tell somebody? What could influence the PR interval? Because the PR interval is not constant. Come on.
Vagus innervation.
I cannot hear you, Mo.
Vagus innervation, because it affects the sinus.
Okay, so the vagus and the sympathetic innervation. So I would say that if somebody has tachycardia, so when you do have a sympathetic stimulation, you have tachycardia and your PR interval is getting shorter. So by the rate and the age, younger one has a shorter PR as an older one. But of course, in an elderly people, they do have a connection between the rate and the PR interval, but it's different one, a little bit longer. However, by definition, never ever the PR should be higher than 0.2. All right? So there's no way. Now, what can cause it? Ischemia, infarction, myocarditis, so that's also anything that can alter the conduction in the between the atrium and the ventricle. Now let's see. This is the okay. Good. This is how it looks like in the YouTube video. You can see that the PR interval is longer. It's rhythmic. However, the PR is longer. This is how you diagnose the first degree AV block. So that's a rhythmic one and the PR is longer. That's it. Now this is how this little cartoon. That's a normal one. And when we do have, let's see, the first degree block is still, let's see, rhythmic. However, the difference between the normal and the first degree, only the PR interval. Okay? That's it. So that's a simple way to understand. Look at this graph. Look at this graph. What you can see here, is rhythmic. Yes, indeed, is rhythmic. Do we have P in front of the Q? Yeah, we do have P's in front of the QRSs. However, it's very far from the QRS. So the PR interval that starts from the beginning of the P till the beginning of the QRS, it's longer than 1 square. So it's meaning that is a first degree AV block. If you can't, this can be 0.2, 0.24, 0.24 plus, let's see, 12, so 0.36. So that's a slow, or a very slow PR conduction. This is another graph, okay? This is another graph. Yes, this is rhythmic, very good. We have P wave in front of the QRSs. However, the PR interval is longer. Anybody can tell me the axis on this ECG? What is the main electrical axis?
Normal.
Well, very good, very good. Now this is how you should start. Look at lead number 1, AVF, both positive, normal. That's it, period. Now, if you want to be more precise, what will be, let's see, the axis? Which is the most equiphasic one?
ABL.
Well, you can say AVL or lead number 1 or lead number 3. Okay, it's about the same. If you do have AVL, that should be around 60 or 30. So close to 60, 30. That's fine. Good. Doesn't matter because both are normal. Okay, now let's see the second degree AV block. By definition, we said that second degree means that some of the P waves are not conducted. So it's meaning that we do have a normal PP intervals. However, there are some P's not followed by QRS. So the RR intervals are not the same. So the RR intervals changing. The atrial rate is higher than the ventricle one. Yes, it's true. This is why we do have arrhythmia. Now, what kind of types we do have? We do have the Mobitz type 1, Mobitz type 2, okay? So by definition, if you remember, Mobitz type 1, the velocity or the conduction speed is slowing down gradually. So the PR interval is getting longer, 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 and after we have a drop P wave. So by definition, the last PR should be longer than a first conducted PR. In Mobitz type 2, the PR intervals are equal, but sometimes we do not have QRS follows the P wave. And if you're looking at the gap, that gap when the P is dropped exactly twice as much as the last RR interval. Now I'll show you. Let's see, this is the Mobitz type 1. Very similarly, what I said so far is identical, all right? If you do see here, okay, maybe I can, how can I go back here? Okay, let's go back. I punched the wrong button. Okay, so look at the PR interval. Here is written 0.16, 0.28. See, the PR is getting longer, further longer, further longer. Oops, this P is not followed by QRS, and start everything from the beginning. In the ladder diagram, you can see nicely how in the AV, the conduction is slowing down and after is not conducted. Okay, and by definition, we said that looking at the last PR interval, which is still conducted, and the first one is not the same. The last one is longer than the first one. This is how you should diagnose. Now, these kind of rhythmically changed conduction abnormalities in Mobitz type 1, they has another name, and that's called the Wenkebach periodicity because it's periodically repeated. These two cardiologists discovered the difference, Mobitz type 1 and Mobitz type 2. One was Wenkebach and other was Mobitz, and they named it after them. So if you looking at, let's see, this is how it looks like on the ECG, on the live ECG. See, normal, longer, 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 and dropped. Normal, longer, longer, and dropped. So this is high, and this arrhythmic, and that's arrhythmic, completely arrhythmic. Or you can point which bit is out of order. So if you mark, for example, get a paper, and put under, let's see, this ECG tracing, and mark the PP interval and shift it, and you would say that the PP intervals are equal. So it's meaning this is not a impulse formation abnormality because this P is not followed by QRS. This is why it's a conduction abnormality. Okay. Now, another one that is difficult to understand, but hopefully you will understand. If you're looking at the RR intervals are not equal. The RR interval is longer one, shorter one, shorter one. So not the PR is getting longer, longer, as why the RR interval is getting shorter. When we do have, let's see, the drop beat, of course, this distance is longer one, but not as long as the twice as the last one. So this interval is shorter than the last RR interval. Now, okay, let's look at. Now this is how it looks like, okay? Come on, good. So as you see here, PR getting longer. Meanwhile, the RR interval is getting shorter. Okay. Now, to understand this, why the RR is getting shorter, you can, let's see, look at this graph. Here we can, let's see, emphasize or measure the RR interval. In the first RR interval is equal, if you look at the PP interval plus the PR2 interval minus the PR1 interval. Okay, that should give you the RR1 interval. Similarly to the other one, and because the PR2 minus PR is bigger than a PR3 minus PR2, this is why the RR1 is bigger than RR2, and that's one, that's one. Now, why is it so important to understand? Because if you remember what I said about SA blocks, SA block, we do not have this, let's see, any kind of ECG sign for the sinus activation. So we do see only the atrial activation. Similarly here, if you want to diagnose the AV Mobitz type 1 block based on the RR distance, but we do have the P, but in SA we don't have. We have only, let's see, the B point. So this is why in Mobitz type 1 block, the RR distance, especially with the drop one, that's as not as twice as much as the last one. This is what you should remember. When we get to the SA block, you will understand, hopefully. Now, yes?
Why is PR after the PR interval after the pitch drop is shorter? And how
Well,
do you explain that it is progressively gets longer?
yeah, that's a very good question. Basically, we don't know exactly, but that some kind of relaxing that is needed because it's not discharged, or maybe this little gap, because the relatively here, I have no idea why, but this is how it's changing. Now, by definition or anatomically, usually this block occurs in the AV node, the proximal part in the AV node, and mostly is a reversible block. So it usually recovers. Iron, drugs, or other can cause this first degree block. Why in the other case, in Mobitz type 2, mostly this irreversible and mostly influences the his. So the conduction, let's see, only the conduction fibers are influenced in Mobitz type 2 block. So that could be because somehow for the nodal tissue, completely different from a conducting tissue. And that can be the, let's see, the explanation why the PR can be somehow elongated and can be shorter after that. So somehow the action potential on the nodal tissues are different one. So if you want to, let's see, understand the why is what could be the physiological or the subcellular explanation or electrical explanation, I would say that write a letter to Tornozzi, because Tornozzi is very, I think it's a has an ex-husband about these conduction abnormalities, and they already fished that, and he can suggest you some reading materials about it. But relatively, as a physician, you don't need to know the exact underlying mechanism, especially maybe it's not true. It's only the scientific approach what they said it. Only physiologically or only a physician what you should do to diagnose a difference between Mobitz type 1 and Mobitz type 2. And why? Because in Mobitz type 1, there is no pacemaker needed. However, in Mobitz type 2, a pacemaker indication immediately. This is why it's very important. As in Mobitz type 1, relatively the patient can recover and a normal conduction can come back. Why in Mobitz type 2, you can have, let's see, a third degree block that develops, and only the ventricular escape rhythm can save the life of the patient. And that is the problem, because the cardiac output is very low and usually is not enough to maintain a normal life. And this is why they're putting, let's see, a pacemaker. Is
Thank
this
you.
okay? Well, this is what I could say only. But I can get you a paper if you wish. So Donotsi had a lecture about 3 years ago about this one, but I'm really sorry I could not understand it, what he said. Okay, now let's see. So this is the ECG tracing, and what you do see here, relatively that the P intervals are equal, but we do see an unconducted P, and the last PR is longer than the first PR. So that's the Mobitz type 1 AV block. Now, similarly to the Mobitz type 1, Mobitz type 2, when, however, the PR is constant. That's it. So it's meaning that, as you see, that usually gets worse and it can progress to the 3rd degree block. But if you look at, let's see, the ECG sign is be that the PR, whenever is conducted, is the same, okay? And you do see some unconducted beats. This is how you can see the difference between these two. Okay, good. All right. Now, and if you look at, let's see, this graph, so the PR1, PR2, PR3 the same, and PP is the same, RR is the same, except when we do have a drop, but this distance exactly twice as long as the last RR interval. This is how would you diagnose a Mobitz type 2 2nd degree AV block. Now, we do have a 2-to-1, very simple. Every second P is conducted, the PR interval should be equal at, it can be Mobitz type 1 or Mobitz type 2, but difficult to diagnose. Basically, we cannot diagnose whether it's Mobitz type 1 or Mobitz type 2 because the last conducted PR and the first conducted PR is the same. Okay, and that's rhythmic, but the rhythm is half as much as the PP. Okay. Now, basically, based on the 12 leads ECG, you cannot diagnose Mobitz type 1, Mobitz type 2 here. And this is why the physician will put the pacemaker immediately into this patient. If you had an intracardial ECG, now you could diagnose it, whether that's a proximal block or that's a distal block that propagates to the 3rd degree block. But because it's a more severe condition, this is why they put a pacemaker immediately into this patient. Okay, this is how it looks like. Rhythmic, rhythmic. Do we have P wave? Yeah, we do have P waves, and the P is coming rhythmically, but not every P conducted. Okay, this is how you diagnose. Okay, high degree block. Now that's a little bit difficult to understand, but hopefully I can explain you. So what does it mean? It's meaning that there are more than 2 P's not followed by QRS complex. So we do have a longer distance between the conducted and unconducted. So mostly unconducted. And what will happen? The ventricle escape rhythm is going to generate the impulse when we do have, let's see, this unconducted. However, sometimes it's conducted. Okay, how do we know that sometimes it's conducted? If you are lucky, you can look at the shape of the QRS complex. These are ventricle escape bits. However, when we do have a capture bit, that QRS complex should be narrow, should be a supraventricular QRS complexes. So it looks like, and this capture bit, this conducted bit, makes it arrhythmic. All right. So sometimes maybe you can hear it. I don't know what I tried to knocking on the desk. Okay. So for example, all right. Okay. So this is the ventricle escape rhythm. Can you hear it? Okay. And sometimes we do have a conducted bit. Okay. And that's conducted bit, or that's called capture bit, makes it arrhythmic. But that's a chance, for example, that the escape bit and the conducted bit comes together. So in this case, we do have, it's called the fusion beat, when the supraventricular beat and the ventricle escape beat activated the ventricle. How do we know that? Because the QRS complex be between these two. So that's be the bizarre shape, but it's not as the same as a QRS complex. And another very important one, it will come in the time of a ventricle escape beat. Okay? Understood? Mostly. Okay, the third degree blocks relatively, that's an easy one, meaning that there is no connection between the P wave and the QRS complex. So what will happen? An escape rhythm will develop depending on where we do have, let's see, this block. If the patient are lucky, this ectopic pacemaker rhythm can originate from the lower AV junctional, and that makes a little bit faster escape rhythm, or it can originate from the ventricle, and that makes it a slower ventricle rhythm. So what will happen? Let's see. That is called AV dissociation. Now, how does it look like? Okay. Here you do see a lot of P's, and very importantly, the PR is not connected to each other at all, and sometimes you do see some P inside the QRS complex, and that can be, the QRS can be wide or can be narrow, depending on the center of the escape rhythm. Now, as you see here, I draw you a ventricle escape rhythm. And as you do see, we do see the P, 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 P interval. Again, getting a paper, underline the paper and mark the P, P interval. And when you shift it, you will see that some P is located inside the QRS complex, or on the top of the, or maybe on the T wave, or inside the QRS. And you can see a little notch or little altered QRS complex. But this PP is the same. And plus it's rhythmic, because you do see a very low, depending on if you do have a ventricle rhythm, that should be around 25 or 30. Why, if you do have a junctional one, it can go to over 40 as well. All right, so this is the third degree. But there's no connection between the P wave and the QRS, and that's rhythmic. So first degree AV block was rhythmic. Second degree AV block is arrhythmic. 2-to-1 AV block is rhythmic. High degree AV block is arrhythmic. And third degree AV block is rhythmic. Okay? Now, let's move on. And now we are going to discuss the SA block. No, this is only the third degree block. Let's see this sign. Very similarly, very low rate of the ventricle. And you do see a lot of P waves. And as you see, we do see a P. We do see a P here. P inside, let's see the T. So there is no connection between the P wave and the QRS complex. Now I do have a, let's see, the hypothetic, let's see, situation. We do have a sinus impulse formation, let's see, of 60. So we do have a rate of the atrium, that the atrial rate is 60. The ventricle escape rhythm can be 30. Yes? So it looks like if you had a 2-to-1 AV block, that means that every second P followed by QRS. Okay, you could say that the QRS complex is wider a little bit when we do have a ventricle escape rhythm, but when we do have a low junctional rhythm, that the QRS complex is not. How do we figure out that this patient has a third degree AV block or only a 2-to-1 AV block? Anybody has any kind of suggestion? Did you understand what I said?
Maybe if we can find the negative P after QRS in case of third degree AV block, that confirms that this is...
Well, it's only one thing. Yeah, it could be, because sometimes the ventricle escape beat, or the beat, it goes backward. But if you do have a block, there's no way that can go back. Okay. So you have to have, let's say, in a premature ventricle beat, very commonly you can see the negative P wave. However, if you do have a third-degree block, there is no way that you can see it. What else? And especially when you do have a 2-to-1, if the conduction goes backward as well, only one problem, that the atrium is relaxed, so it cannot accept the charge. No, what else you can use? You can do anything with the patient to make the differentiation between these two. So how can we prove that, yes, there is a connection between the atrium and the ventricle? Because third degree, no. In 2-to-1,
We
yes.
do some, I don't know,
No, come on, come on, come on.
carotid maneuver.
Carotid massage. Yes, you can use carotid massage if you want. You can apply vagal maneuver, and that meaning that is going to slow down, let's see, the PR conduction. That's good, means that you do have maybe a little bit higher grade of the AV block. But when you do have a ventricle one, a third degree, there won't be any effect on it. Any. Or another thing, you can increase the sympathetic activation. For example, ask the patient to wake up and do some exercise, for example, and apply, let's see, or look at only the pulse. Look at only the pulse of the patient. Because if the patient has, let's see, the third degree, the pulse won't change at all. No way. However, when you do have a connection between the atrium and ventricle, yes, you will have an acceleration of the heart rate. Okay, good. Let's move on. This is very similarly, but here we do have a little bit wider QRS complex. Okay, assay blocks. Now that's a little bit difficult to understand. But let's look at when we had AV block. If we had block, the P is not followed by QRS complex. Okay. When we have assay block, what we are going to miss? The P wave. When we do have unconduction from the assay to the atrium, there is no P wave. That's it. So the difference is when we evaluating the AV block, the connection between the P and the QRS, and usually P is not followed by QRS. Why we do have an assay block, relatively, when we have P wave, we have conduction. When we have no conduction from the assay, there is no P wave. That would be similar to the sinus arrest. So meaning no P wave, but there be a different. Now let's see, and what will happen when we do have a first degree. I think it's, yeah, that is what I explained. Good, go on. Let's see the classification. The classification, when we are talking about the first degree block, relatively every sinus impulse is conducted, but slower. But because we don't have any sign of the sinus activation, there is no sign of this block. Because we do see only the P wave. We have no idea how fast, let's see, this impulse getting to the atrium. So that's be rhythmic, and we do see nice P waves. However, we do see sign for the second degree assay block. What? We do see PPP, but sometimes the P's are missing. And the third degree, there is no P wave at all. And we do have a junctional escape rhythm, but you don't see the sign of the P wave. So the difference between a third degree AV block and a third degree SA block B, in third degree AV block, we do have P, 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 and independently from the P, we do have a QRS coming regularly, an escape rhythm that originated from the ventricle or from the AV node, or lower AV junction. However, when we have a third degree SA block, straight line, and you do have a junctional escape rhythm or ventricle, but mostly the junctional escape rhythm is coming. Is it clear?
Yes.
Okay, good. Let's look at what we have here. That's a third degree possible. That's a third degree, or this is not a third degree, that's a second degree. See? when we do have normal conduction, and after when we don't have P wave. That's a SA block, a second degree SA block. Okay. Up. Good. Now let's see how we diagnose it. Let's see the Mobitz type 1. And now I'm going to refer what I said about Mobitz type 1 AV block when we looked at the QRS complex. However, here you have to look at the P waves. The arrows pointing when the SA is activated, okay? And this is only the atrial activation when we do have the P waves. So when you're looking at the P intervals is getting shorter. Why? When we do have the dropped SA activation, there is no P wave at all. So relatively, this distance is less than twice as much as the last one, because the PR is not altered, because it's not an AV block. This is why the RR is following the PP intervals. Okay, so in the SA block, Mobitz type 1, you can look at, first of all, do we have P waves? Oh, we don't. But the RR intervals are getting shorter, or the PP intervals are getting shorter. Okay? It's clear?
Yes.
I'm sorry.
Yes?
Why is the PP interval getting shorter?
Because very similarly to the AV junctional block when we discussed it. If you go back and measuring the distance between, let's see, the PR, how the PR is changing, and how, let's see, the RR is changing, what I said at that time, you will understand in Mobitz type 1 AV block, the RR is getting shorter. It's very similar. However, I cannot point which is the sinus activation. But that's be identical where in AV block we had the RR changes. Here, the PP changes is the same.
Yeah.
Okay. Now, here, for example, this is what it's drawing, that you do have, let's see, the PPs are getting shorter, very similarly to the RR, because the PR is the same. And when we do have a dropped, you don't see any P wave. But that distance is shorter than twice as the last one, very similarly to the AV when you look at the QRS complexes. Now, in Mobitz type 2, what happened in Mobitz type 2? In Mobitz type 2, the PPs are identical, except when we do have this unconducted one, that should be twice as long as the last PP or the last RR. So this is how you diagnose. So the difference between the AV and the SA block, here we have no P wave when we have the block. In AV, we have no QRS following the P wave. Okay? Good. Now, this is how the second degree Mobitz type 1 block looks like. Again, that is arrhythmic. That is arrhythmic. And if you are looking at maybe, okay, when you're looking at the distance, see, it's getting shorter. And this gap is different or less than twice as much. And this is how you can diagnose that that's a let's say SA block, because there is no P wave. Okay, there is no P wave is missing here, and after is coming back. Okay, and that's the second degree and Mobitz type 2 SA block. Here relatively is identical, the PP and QRS, and this is twice as long as, oops, what I had. Okay, and that's twice as long as the last one. Okay, that's the second degree with a ladder diagram. You can measure the distance here. There's no P wave at all, but this should be twice as much as this one. Good. Any questions so far? I know it's not an easy one. And this is why I asked you to watch the video. And now maybe a little bit be easier to understand again. And you'll be prepared maybe, and you will have some idea what the difference between these blocks. Now, let's see and let's reach the ventricle. Now, inside the ventricle, we have branches, bundle branches. If you recall your anatomical study, you see that from the his, after the his is divided into the right bundle branches and the left one. The left one composed of a posterior and anterior fascicle, and they do have a septal fascicle as well. Now, what will happen if we do have a block here? Now, this block can be first degree, second degree, anything. But mostly when you diagnose, let's see, bundle branches, that's a complete block. This conducting system is very sensitive to hypoxia. So the mostly a hypoxic changes is going to cause a block or bundle branch blocks. But sometimes you can see that every QRS complex is the same and altered and showing the typical pattern of the right bundle branch block or left bundle branch block. But sometimes the patient has a normal QRS complex, and sometimes they do have the typical pattern of the right or left bundle branches. That's the second degree, let's see, bundle branches. And mostly because the repolarization influenced by hypoxia, mostly they're the rate dependent branches, meaning that the second degree, because if you have less time for the repolarization, yeah, that's, for example, branches can be blocked. Now, what type of bundle branch blocks we have? We have, it's called the right bundle branch blocks when we have no conduction in the toward the right bundle branches. And what will happen? Only the impulse activates the left side first, and after the muscle conduction is going to activate the right side. Now, the left bundle branch block is the opposite one when we have the right one, but we don't have the left one because different coronary supplies these different areas. And okay, the right one activating the left one. Now, this hemiblock can occur, not the all left bundle branch is blocked, not here or not, but maybe it's blocked, for example, in the anterior part or maybe the posterior part. And this is why we can have this called hemiblocks. We can have it's called bifascicular block. Bifascicular block meaning that that's two fascicles is blocked. One is always the right bundle plus anterior or posterior. This is what is called bifascicular block. So we could have a typical pattern of the right bundle branch block together with the sign of an anterior hemiblock or the posterior hemiblock. We can have trifascicular block as well. Well, why not? The trifascicular block means that we do have a bifascicular block, plus we do have an AV block. And this mostly due to ischemia. This is what you have here. Okay, now let's see the normal depolarization of the ventricle. The first part is the septum. The septum is activated from the left bundle. And this is why the impulse goes from left to the right. This is why we do have a positive wave in V1 and a negative in V6. The next one, the left and the right side activated together, but because the left one is thicker, electric activity about 10 times higher, we do see a vector that pointing from right to the left. This is why on left side we do have a tall R wave, and in V1 we have a deep S wave. This is why we do have an RS complex normally in V1 and the QR complex in V6. Now, you learn in physiology that is called the ID time or ventricle activation time. The ventricle activation time or the ID time is the time that is needed for the activation of the muscle that underlies the electrode. So it meaning that from the beginning of the QRS till the highest or the last R wave in the QRS complex. As you do see here on the right side, because only one way normally, that is a septal activation, goes toward the right side. This is the ID time or ventricle activation time, only the septal activation, and that's be less than 0.2 seconds, so it's less than 1 square, 1 millimeter. However, on the left side, this is the bigger or the next big vector, that's the ventricle activation, so the top of the R wave. And that should be around 0.06, so it means about 1.5 millimeters normally. So this is the normal width. For sure, the ID time is not the same in all leads. So that's the different one. But when you do have any kind of possibilities to have bundle branches, look at V1 or V6, the right side and left side. Okay, let's see what will happen when we do have a right bundle branch block. Okay, what do you think? Is the septal activation altered when we do have a right bundle branch block?
No.
No. Yes. So meaning that we still have a normal septal activation, meaning that we do have a positive R wave in V1 and negative Q wave in V6. What will be the next one? Well, the left side activation, that's be very fast. So very similarly, in the normal situation, we do have a deep S wave in V1 and a tall R wave in V6. But what will happen with the right side? The right side activated later through the muscle. So that means we do have a later coming activation toward the right side. So again, we do have a R wave and wide R wave in V1 as a deep S wave, wide S wave in V6 on the left side. So if you're looking at the intrinsic deflection or ventricle activation time, you do see that in V1, it's much bigger because the first one is the septal activation should be the normal. But here we do have an other big R wave. So that's ventricle activation time is elongated on the right side. However, here, the R wave is still normal because it's not altered. That's left ventricle activation. But we do have a deep S wave, a slow S wave, slurred, slow S wave. So this is how you diagnose a right bundle branch block. Now, okay, so this is a summary, what we already said. The septal activation could be normal, and left side the activation is normal. Only the right ventricle activated through the left ventricle, and the shape of the QRS is notched in V1 or V2. Okay, now, by talking about the bundle branch blocks, if the QRS is wider than 0. Let's assume 0.1 second, that you do have a complete bundle branch block. However, if the QRS complex is not wider than 0.12 second, but you do have the typical pattern of a right bundle or left bundle, that's called incomplete block. Because we do have an abnormal activation of the ventricle, especially in right bundle branch block, we do have an abnormal activation on the right side. For sure, we do have a secondary repolarization abnormalities. So this is why we do have a secondary STT changes in a case when we do have bundle branch blocks. Now let's see how does it look like. Okay, so this is the typical pattern of in V1 RSR or notched R. Sometimes you don't see this RSR complex in V1, only do see a wide R wave in V1. But in V2, you do see some notching as well. This is how you diagnose. So I would say that if you want to diagnose, let's see, right bundle branch block. If you do see that the QRS complex is wider, let's look at V1 and V6. Whenever you do see the wide R wave, the block is there. That's it, period. You can follow any kind of written, let's see, suggestion. For example, in some books says that, okay, let's look at the shape of the R wave in QRS complex in, let's see, V1. This looks like as an M. If you do see the M in V1, that's a right bundle branch block. If you do see in V6, that's a left bundle branch block. And if you look at, because it's 6 letters is coming all the way here, that's a Moreau. This looks like a W for you. Okay, that's a Moreau phenomenon. Okay, but very difficult to see this Moreau phenomenon. Now, here, very similarly, look at in V1, RSR, that's a typical one. Okay, and the deep S wave and wide S wave in V6 or in the left side in lead number 1, lead number 2. That's it, period. Now, this is what I mentioned about the incomplete. If we do have the typical pattern of the RSR complex in V1, but the QRS is not wide, that can be the incomplete right bundle branch block. That's mostly due to the stretching of the right side, or coronary diseases, or defect, or ventricular diastolic overload, and so on and so on. Now, let's see what will happen when we do have the left bundle branch block. Now, in the case of the left bundle branch block, the septal activation is altered. 90% of the impulse coming from the left side and 10% from the right side. So the septum could be activated only from the right side. This is why at the first moment we do have a negative wave in V1 and positively starting in V6. For sure, because the septum is a left ventricle, part of the left ventricle, this is a starting point. Sometimes you can see the right ventricle activation, but sometimes you don't. And sometimes you do see a notching in the, let's say, in the V1 or notching in the V6. But the major activation that's happening through the muscle, that's pointing from right to the left. This is why you do have a QS complex or a W, let's say letter of W in V1, and an M complex in V6, or I would say that wide R complex in V6. Again, if you look at, let's see, the ID time or ventricle activation time, you can see that this is elongated on the left side. So the left side. This is why that's a left bundle branch block. Now here they say that that's a William. That's a William started with W, and in right bundle, that's a Moreau, whichever you like. But I think the easiest one to understand, whenever you do see the wide nudged R wave, the block is there. Okay. Now, however, to diagnose a left or right bundle branch block, you have to have supraventricular rhythm. So the charge should come from the atrium or from the AV. Because if you had a ventricular escape rhythm, there is no way that the charge, let's see, enters to the bundles. The bundles can be reached only from the AV, from the bundle of His, okay? So mostly you do have a P wave in front of every QRS complex, and the QRS is altered, okay? Okay, this is identical what I said. All right, I don't want to go through, but this is the summary what you have, and this is how the ECG looks like. As you see in V1, that's a QS complex, wide QS complex, and we do have a P in front of, let's see, the QRSs. Very good. Now, here, again, we have to show that we do have a P wave in front of every QRSs, okay? And we do have wide QRS. Look at V1. Wow, QS. And in V6, let's see the wide R wave. And here you can see only in lead number 1, the nudged R wave, okay? Now, what about the hemiblock? Now, what about the hemiblock? The hemiblock usually is not going to widen the QRS complex. So the QRS be narrow. However, because these bundles, the anterior and the fascicles is located differently. Let's see, the anterior fascicles runs from left to the right on the front of this ventricle, while the posterior is running on the right to the left and of the posterior on behind of the heart. Now I'm going to turn on my, let's see, camera. Okay, and I stop right, see here. Okay, now hopefully I try to, I don't know where you do see me, possible you do see me in the middle, hopefully. Okay, all right, come on, I can, okay. All right, speaker view, no, I don't see the speaker view. That's good, very good. Now, only one thing that maybe I'm going to pause a little bit. Okay, let's continue with the hemi blocks, okay? Okay, good. So basically, the difference is only with the axis. So if you do see an extreme left deviation, that caused by an anterior hemi block. If you do see an extreme right deviation, that possibly due to a posterior hemi block. Now, come on. Doesn't want to change. Oh, looks like my PowerPoint is. So, looking at this graph, what can we see here? Well, rhythmic, most of here is not rhythmic. That's a premature bit, as you see here. But let's see the axis. 1 is positive, AVF is negative, 2 is negative. That's an extreme left deviation. So that's a left anterior hemi block. Great. What about the posterior hemi block? The posterior hemi block, exactly the opposite. We do have an extreme right deviation. Okay, good. Look at this one, the axis, everything is identical. The QRS complex is narrow, everything. 1 is negative, great. AVF positive, so we are on the right quadrant, right lower quadrant. That can be a posterior hemi block, period. So based on the axis, we can diagnose anterior and posterior hemi block. This is why we measure or calculate the main electrical axis for diagnostic process. Okay, look at this one. That's a bifascicular block. What did I say about the bifascicular block? I said we do see a right bundle branch block and an anterior or posterior hemi block. The anterior is more common one because the right bundle and the anterior part of the left bundle is supplied with the same coronary. And if it's clot or if it's somehow suppressing the circulation, that altering these two parts. What we see? We see a typical pattern of the right bundle branch block. In V1, you do see this RSR complex. In V6, you do see this wide S wave. And look at the axis. 1 is positive, AVF is negative, 2 is negative, extreme left deviation. So together with the right bundle branch block with an extreme left deviation, the diagnosis is a bifascicular block. The next one, similar, typical pattern of the right bundle branch block, okay? And as you see here, I think that's a wrong one. That's a wrong one. You should see a big, in the lead number 3, you should see a big R wave, and this is not that one, so it's a wrong one. I don't want to show you. Now, trifascicular block means that we do have a right bundle branch block, a left anterior hemi block or posterior hemi block, plus we do see a first degree AV block. So if you're looking at the PR interval is very long. So typical sign of a right bundle branch block, axis is extremely left deviated or right deviated, and first degree of AV block. This can be the trifascicular block. Trifascicular block can be, for example, this is what I mentioned, okay? plus left bundle bench block together with the first degree AV block. That can be, again, a trifascicular block, and alternating the right bundle and the left bundle. So some bit follows in the sign of a right bundle and another one follows the left bundle. That can be typical. Here you can see that's a left bundle bench block, very nicely, okay? And in V1, sometimes you do see the right bundle bench block, and sometimes you do see the left bundle bench block, and the PR interval a little bit elongated. Okay, good. And rate dependent, this is what I mentioned. If sometimes, if you do see, let's see, some repolarization difference between the right and the left side, if you do have a higher rate, you can see immediately that every bit be the pattern of the right bundle bench block. However, in another lower rate, you can see some normal bits, and after some abnormal right bundle bench block pattern can develop. Now, so far what we discussed, these were about slower conduction. We can have, however, faster conduction. Only one side in the heart where we do have a slow conduction is the AV node, in the AV junction. In some case, we do have some abnormality, some additional fascicles, so that's a hereditary abnormality, when these bundles or fascicles connecting or bypassing the AV junction. The most common one usually is WPW syndrome and LGS syndrome. The Mannheim types usually is less common one. So we are going to discuss with these two. And why is it important? Because that can serve as an arrhythmia. So that can cause arrhythmia to the patient because we do have two parallel pathways, conduction, with different, let's see, velocity or different refractoriness. Now let's see the first one. That's a very common one. It's about 4% or 7% to the population. That's an inborn error. For example, the pussycats, they do have much more, this can bundle. This can bundle is connecting the atrial muscle to the ventricle muscle. So relatively, the annulus fibrosis is bypassed with this can bundle. So what will happen? When we start to activate, let's see, the atrium, we do have a P wave. But right after the P, the ventricle started to be activated. So we do have a slowly starting wave. And however, meanwhile, the AV conduction reaching the bundles and activates the last part of the QRS complex. So what we had, PR is short and the QRS is wide, and you do see this delta wave. This is what you will see when you do have this WPW syndrome. So short PR and wide QRS complex. Now there are two different types of WPW depending on where this bundle is located. If the bundle is located on the left side, this is the A type. If it's located on the right side, that can be the B type. This bundle can be anywhere. And of course, they have to determine where the bundle is located. Now, to diagnose, look at V1. If you do see a positive wave, that meaning that's a A type. And if you do see the negative one, that's a B type. This is what you have to look at it. See, for example, here you do see the A type and the following one, that should be the B type. Now, by looking at, let's see, this PR interval, very short, and you do see a notching in the first part of the QRS complex, but you have to look through the all 12 leads. And sometimes not every lead has this nice delta wave. This is why you have to follow it. Now, LGS, come back. LGS syndrome is different one because LGS syndrome says that, okay, this James fiber is bypassing the AV junction and the fiber connecting the atrial muscle to the bundle of His. So what will happen? The P followed by QRS immediately, but because the ventricle activated right away through the bundles, that QRS complex be narrow. So this is how you can diagnose this LGS syndrome. Now, what will happen with this pre-excitation syndrome? As I mentioned, relatively that can activate or can form is called AVRT tachycardias. So paroxysmal tachycardias can develop when we do have this re-entry phenomenon. And that's can followed by fibrillation or atrial flutter as well. Now, let's see what will happen. This AVRT tachycardias or atrioventricular re-entry tachycardias, that when we do have the accessory bundles. Now, these bundles can take the charge back to the atrium, and this is how you have this re-entry cycle, or can activate the ventricle and AV junction can reuptake the charge. So based on this WPW syndrome, we can have two types of paroxysmal tachycardia. One type when we have a narrow QRS complex, narrow, completely narrow, looks like it's a supraventricular tachycardias. You don't see the delta wave because the delta wave is reuptaking the charge only, okay? That's an orthodromic one. And when you do have, when the ventricle activated through the bundle of CAN through the muscle, you do have a wide QRS tachycardias. And that's the antidromic AVRT tachycardias. Okay. Now, this is, for example, that's an antidromic when you do have a wide, and these are almost identical with the ventricular tachycardias, but is not. How do we differentiate between a ventricular tachycardia and a antidromic AVRT tachycardias? That's an orthodromic. What do you think? With carotis massage. Carotis massage. A patient will know it immediately because the patient suddenly develops tachycardia and starts to massage the neck or Valsalva maneuvers, everything. And because we do have two parallel pathways, and these pathways includes, let's see, the AV node. This is why the sympathetic stimulation or vagal tone altering the conduction speed and can stop, let's see, the tachycardias. Now, another one that I already mentioned you when we discussed the AV junctional tachycardias or proximal junctional tachycardias, that's the AV NRT tachycardias. So this re-entry cycle develops inside the AV node in different parallel pathways. So this usually cannot be stopped by carotis massage, and they always have the narrow QRSs, okay, narrow QRSs. This is a difference between the AV and RT and AV-RT tachycardias. This is how mostly the supraventricular tachycardias is mostly AV and RT tachycardias. To diagnose an AV-RT tachycardias, at rest the patient will have WPW syndrome. This is how you would diagnose it very easily because you do see the sign of the delta wave and the short PR, and after the tachycardia develops, that's an AV-RT tachycardias. Okay, so any questions? Wow, every